Hello and welcome to the final lab of Physics 2, lab number 5. In this lab, we measured the amount of time that a magnet took to fall through a ball of aluminum foil and then built a computational model to recreate that situation and hopefully acquire the same result for the amount of time that the magnet takes to fall through the tube. And the reason why this problem is interesting is because the magnet falling through a tube of aluminum experiences magnetic braking as the charges in the aluminum move to counteract the movement of the force of gravity down on the magnet. So the main thing that we use to predict how that magnetic braking would occur is Faraday's law, which states that the change in magnetic flux across a surface is related to the circulation of the electric field around the boundary of that surface. And what that means at a high level is that this changing magnetic field of a magnet falling down is going to be able to induce currents to move in the aluminum foil, which will in turn create their own magnetic field to oppose the movement and oppose that change in flux of that magnet. Now, the way this experiment worked is fairly straightforward. We dropped a magnet through a roll of aluminum foil and measured the amount of time it took to get through. We took 3 different measurements and averaged them to arrive at some final time, an average time estimate for how long the magnet took to fall through the tube. And then after this, we built a computational model that made use of Faraday's law to predict how that magnetic braking would occur. And as you can see here, the magnet at first accelerates due to the force of gravity, but then as it reaches a higher and higher velocity, the force moving against the force of gravity, the gravitational or the magnetic braking, increases until we reach a constant speed. And of course, in this case, the system would be our magnet, the surroundings would be everything else. Well, I suppose the system would be the magnet and the foil, and the surroundings would be everything else. And the initial condition would be with the magnet at rest at the top of the aluminum foil. So we built our computational model, and we found that it matched up fairly closely with what we experimentally measured as far as the time that the magnet took to fall through the tube. And one major difference here would be that we're not factoring in air resistance, and air resistance would be proportional to the velocity squared, so this velocity would probably be a little lower in reality than our computation model would predict due to air resistance. Now, for the questions. The what if question, asking about if the resistance in the aluminum was 0 or very, very close to 0. And as the resistance in the aluminum gets closer to 0, our computational model would predict that the magnet would fall slower and slower and slower through the tube. And in the limit, where there is no resistance, such as in a superconductor, the magnet would actually not move at all. It would be locked with the aluminum foil, and we would call this quantum locking of the superconductor with the magnet. And for the other what if question, what if holes were poked in the aluminum foil? These holes would interfere with current flow and thus increase or reduce the maximum magnetic field that the tube could generate to oppose the movement of the magnet, and so the terminal velocity of the magnet with that magnetic braking would be faster. Thank you.